Hey everybody, welcome back. This is CHEM300 and we're continuing chapter 4 today with talking about elements. Elements are defined by the number of protons they contain. So in the last section, we talked about the subatomic particles, the protons, the neutrons, and the electrons. We're going to talk more about those as we continue talking about elements, eventually about ions and isotopes. So we're going to start with elements, which are defined by the number of protons in the nucleus of an atom. So previously we talked about elements when we were subdividing and classifying matter according to its composition. We said that elements are pure substances that cannot be broken down into simpler substances. And that's true. We're going to continue to use that definition, but we can add to it and further refine it. Now that we know about subatomic particles, about protons, neutrons, and electrons, the definition of an element can be further refined. Elements are defined, given their identity, based on the number of protons in the nucleus. So for example, if you have 2 protons in a nucleus, by definition, that's going to be a helium atom. If you have 13 protons in the nucleus, by definition, that's going to be an aluminum atom. So based on the number of protons in the nucleus, we can define the identity of each of the elements. So elements are defined by the number of protons in the nucleus. Each element on the periodic table is going to have a different number of protons in its nucleus. There's currently 118 elements known. They each have a different number of protons. If the number of protons in an atom changes, the identity of that atom changes. It's no longer an atom of the same element. It would be a different element if the number of protons changed. So the number of protons in the nucleus is very important in chemistry. It's what identifies each of the individual elements and atoms of that element for us. The number of protons in the nucleus, we give a special term that's called the atomic number. It's the number of protons. And we use the symbol Z to represent atomic number. So let's dig into this new definition or refined definition of an element. An element is a pure substance in which all the atoms present have the same atomic number. Remember, atomic number is the number of protons in the nucleus. So for example, all atoms of carbon are going to have 6 protons. The atomic number of carbon is 6. That means any atom that has 6 protons by definition is going to be carbon. If we add or subtract any protons, it's going to change its identity into a different element. For a neutral atom, because neutral atoms have 0 charge overall, the number of protons is also going to be equal to the number of electrons. Each proton has a charge of +1. So if the atom is charge neutral overall, if you have a certain number of protons, then you have to have that same number of electrons for the charges to add up to 0. So for neutral atoms, the number of protons and the number of electrons is equal. So this is the typical symbol of an element on the periodic table. There's some parts to it we'll talk about. Oftentimes, the biggest number in the box is the atomic number, represented by the letter Z. This gives us the number of protons in that atom. This is what defines what element we're talking about. Hydrogen is always going to have 1 proton. If we added a proton, we had an element now with 2 protons, it would no longer be hydrogen, that would be helium. Then you have the element symbol. This is going to be 1 to 2 letters. And you do uppercase for the first letter. If it's a 2-letter symbol, then make sure your second letter is lowercase. It can get very confusing if you accidentally use uppercase for both letters in a symbol, because it can make it look like it's 2 different elements. So the first letter of the element symbol is always uppercase. And then if it's a 2-letter symbol, the second letter is always lowercase. Then you have the element name, and then the atomic weight of the element, which has units of atomic mass units. We're going to talk about how to calculate this towards the end of chapter 4. So on the periodic table for the elements, each element has a unique name. They're usually and oftentimes named for important places, the people who helped discover them or whose scientific discoveries led to the discovery of that element, or Latin words or other language translations that are related to the properties of that element, like what it looks like or smells like or feels like. Each element has a unique symbol. It's going to be a 1 or a 2-letter symbol, and the first letter of the symbol is always capitalized. Each element also has a unique atomic number. Remember, atomic number is the number of protons. So for each element, it has its own unique number of protons. If that number changes, you're dealing with a different element. So atomic number, number of protons. To give you kind of some history and background of some of these names and symbols of the elements, early scientists often gave newly discovered elements names that reflected their properties. So for example, argon comes from the Greek word argos, which means inactive. Argon is one of the noble gases. It doesn't like to react with other atoms or elements. It's very unreactive. So it got that Greek name, argon, based on the Greek word argos, which means inactive. A lot of other elements were named after countries or places. Polonium was named from Poland, francium after France, americanium from the United States of America. We have berkelium and californium. We've discovered a lot of elements in the Bay Area at the Rutherford and particle accelerator labs there. Other elements were named after scientists. Curium was named after Marie Curie, and Rutherfordium was named after Ernest Rutherford. And just a note on Marie Curie, I put hearts here because she's one of my science crushes. She did like absolutely amazing work in the early 1900s studying radioactivity. And it was a very difficult time for women to be scientists. She had to oftentimes get things done through her partner, who was a professor at the university. It was only through him that she was able to kind of get access to a lab and access to the materials she needed. And actually for quite a while, her lab was in the garden planting shed next to the chemistry building. She wasn't allowed to have a lab inside the building for many, many years. And despite all those challenges, she was really able to overcome and continue her work, and was really one of the parents of our understanding of nuclear chemistry and radioactivity. So here's a few elements and symbols that have names that don't match what you might think they will be. Symbols that don't match the beginning of the English spelling of the word. So lead, its symbol is Pb, comes from the Latin word plumum. Mercury, you think that its atomic symbol would be Ne, but it's not, it's Hg, comes from hydroguranium. Iron, you'd think that its atomic symbol would be something like Ir, but it's not, it's Fe, and that comes from the Latin word ferrum. Silver symbol comes from argentum. Tin symbol Sn comes from stannum, and copper symbol Cu comes from cuprum. So a lot of the symbols that don't match up with how the word is spelled nowadays, those symbols are historic. They're related to the Greek or the Latin words for those elements. And then that was turned into the symbol. So I put some resources here to help you become more familiar with the elements. There's an interactive periodic table from WLONK.com. It's really cool because you click on the different elements to learn interesting facts about them, like how they're used in everyday life. There's a great interactive periodic table also from Scientific American. This one has more detailed facts about each element. You click on the elements and it opens up like a whole page just about that element. And then this last one, I'm going to put 2 stars, actually like 4 stars next to. This is an interactive periodic table from ptable.com. And especially if you go on to future chemistry classes, this periodic table is going to be your best friend, because you can click on each element for a list of its properties like melting point and boiling point and all the properties of that element, hardness and size. But it also has a section of the periodic table that gives you the electron configurations. And orbitals. And we're going to talk a little bit about electron configurations and orbitals in chapters 9. And then if you go on to Chem 400, you spend a lot of time in that class talking about configurations and orbitals. And ptable.com has an interactive periodic table that you can click on each element, and it gives you specifically information about both those things. Okay. So some chemical symbols are going to include an additional piece of information called the mass number, which we abbreviate with the letter A. So here we have our chemical symbol. I made up an element called mediapium. gave it the symbol M. The atomic number, if the mass number is also going to be listed, the atomic number is going to be lower left next to the element symbol. So atomic number is the number of protons. And if the symbol also includes the mass number, that's going to be on top of the atomic number. And the mass number is the total number of protons plus neutrons. So this is going to be a bigger number. And this one, because it's just the protons, this is going to be a smaller number. So this mass number, again, is the total number of protons plus the number of neutrons in the atom. So the mass number is the number of protons plus the number of neutrons. So if you want to calculate, say, just the number of neutrons in an atom, you're given the mass number. And because you know the identity of the atom, you either know the number of protons from the atomic number, or you know its symbol. And if you know the symbol, you can look up the number of protons on the periodic table. We can calculate the number of neutrons. So if you want to find the number of neutrons, you're going to rearrange this equation to solve for neutrons. So you get mass number minus number of protons equals your number of neutrons. And we're going to get some practice doing this. You'll get practice doing this in the homework as well. That's why mass numbers are very handy. You always know the number of protons based on the identity of the element. If you're just given the symbol, you've got to use the periodic table, look up that symbol, and then check the atomic number on the periodic table to get the number of protons. And then if you're given the mass number, you can calculate the number of neutrons. Or if you're given the number of neutrons, you can add that with the number of protons to calculate the mass number. And then down below comes the atomic weight. Notice that a mass number and atomic weights are different. I know when I was learning chemistry, I used to get these confused all the time because they both sounded like they had to do with like weight and mass. Mass number is always going to be a whole number because you're counting the number of protons plus the number of neutrons. So how I remembered was that the mass number, it's always going to be a whole number because you're just counting all the protons plus all the neutrons. The atomic weight, we're going to calculate that. And because it's going to be calculated based on averaging the weights of different isotopes of the same element, it's going to be a number that has some like decimals after it most of the time. So that's how I would keep them kind of clear. Mass number, just counting the number of protons and neutrons versus atomic weight, this is calculated. So it's not usually a whole number. So there's different ways to write chemical symbols that include this mass number. And again, mass number is number of protons plus the number of neutrons. The way I just showed, you write the element symbol large, and then upper left, you write the mass number, and then lower left, you write the atomic number. So for example, if we're dealing with carbon 14, carbon always has 6 protons. By definition, that's what makes it the element carbon. So the mass atomic number is going to be 6. And then if it had 6 protons plus 8 neutrons, its mass number would be 14. So we'd write 14 here. The other way to write that, including the mass number, is to put the chemical symbol first and then the mass number second. So another way to say carbon 14 would be C14 or carbon 14. And these are all equivalent. They're all giving you the same amount of information. In these lower two, even though it doesn't explicitly tell you the number of protons, it tells you that we're dealing with carbon. So it must have 6 protons. So we could figure out the number of neutrons. You take the mass number minus the atomic number would give us 8 neutrons, which we found right there also. Let's do some practice with these chemical symbols. For each of the elements below, let's identify the element and the mass number. And then let's calculate the number of protons, neutrons, and electrons for a neutral atom of that element. So we have nitrogen 15. So we want to identify the element, it's nitrogen. And we want to identify the mass number, it's 15. And now we want to figure out the number of protons, neutrons, and electrons in this nitrogen with a mass number of 15. So nitrogen, by definition, checking the periodic table for its atomic number, always has 7 protons. To figure out the number of neutrons, we're going to take 15, the mass number, minus 7. The atomic number gives us 8 neutrons. 8 neutrons. Write that the same way as I wrote protons. And then last one, the number of electrons. And we have a big hint here. It says for a neutral atom of that element. So for a neutral atom, all the positive charge from the protons plus all the negative charges from the electrons add up to 0. So for a neutral atom, the number of protons and the number of electrons is equal. So we would have 7 electrons because we have 7 protons. These match or neutral. Okay, let's do the next one, Cl35. See if you can check your periodic table, find out what element Cl is. So let's work through this one. Cl is chlorine. Just a convention, element names are not capitalized, chlorine, unless they're at the beginning of a sentence. Its mass number is 35. That was given in this way of writing the symbol. So by definition, check how many protons chlorine must have. Look for the atomic number on the periodic table. Chlorine has 17 protons. So if the mass number is 35 and we have 17 protons, to find the number of neutrons, it's 35 minus 17. So we have 18 neutrons. And this is a neutral atom of chlorine. So if we have 17 positive charges from the protons, we must have 17 negative charges from the electrons. So we must have 17 electrons. Okay, next one, Au-196. Find this element on the periodic table. Identify what element it is. Au is gold. And its mass number is 196. So now if we figure out the number of protons, by definition, check the periodic table for the atomic number of gold. Gold has an atomic number of 79, so it has 79 protons. We want to calculate the number of neutrons. We're given the mass number and we know the atomic number, so we take the mass number. This is all the protons and neutrons added up. Subtract out just the protons and that will give us the number of neutrons. So 196 minus 79. This has 117 neutrons. And because this is a neutral atom, it means overall the atom has a charge of 0. So as many positive charges as we have from the protons, we must have that many negative charges from the electrons. So since we have 79 protons, we must also have 79 electrons. Last one, U-235. Let's figure out what U is on the periodic table. It's uranium. So we have uranium. Its mass number is 235. And then if we want to figure out how many protons it has, let's check its atomic number on the periodic table. Uranium has 92 protons. If we want to figure out the number of neutrons in this isotope, in this atom of uranium, we take the mass number because that's the protons plus the neutrons, and we subtract out just the protons. So 235 minus 92. This is to calculate our number of neutrons. 235 minus 92 gives us 143 neutrons. And now the number of electrons. Again, we want a neutral atom, so our number of protons and electrons has to be equal. So we're going to have 92 electrons. Okay, in our next section, we're going to talk about the periodic table. We're going to talk about a little bit of its history, how it was set up, how it's currently set up, and the different patterns that it shows, as well as parts of the table. So I'll see you then. Thanks for watching. Bye.